Okay, we have Homer and the vertical circle. So the text of the problem is Homer Simpson is attempting to ride a motorcycle around a vertical loop with a radius of 5 meters. In other words, he starts on the ground and rides up a curving path until he's completely upside down and then comes back down again. Think of the Simpsons movie if you've seen it. Homer is maintaining a constant speed as he whizzes around and around the loop. Okay, so constant V. A. List the forces acting on Homer at the top of the loop here. Draw a diagram of these forces in your written work. Okay, so he is touching the interior of this loop. So that means that there must be some normal force acting on him. Technically, that interior surface is touching the motorcycle and then the seat is touching Homer, but we're not asked to make those kind of distinctions here. So we'll just write in a nice normal force towards the center. And of course, gravity is also acting on Homer, and that'll also be towards the center of the circle. And then you could add in some other ones. Obviously, there'll be some propulsive force from the engine of the motorcycle, and there'll be some opposing force, because of course he's maintaining a constant speed, perhaps rolling friction and things like drag, so I'll call it F dot D, or sorry, sub D. Okay, that works, and you would list those out on the quiz, and you'd be all set, all right? Now, for B, in what direction is his acceleration at the top of the loop, and in which of the forces you listed in part A cause this acceleration? Okay, so this is centripetal acceleration because he's going in a circle. And we know always toward the center of the circle. So if he's at the top there, then it would be acting down. If he's halfway down the side, it would be acting to the left or the right, depending on which side he's at. Okay. And at the bottom, it would be acting upward towards the center of the circle. And in terms of the forces that would cause that, well, only two of those forces have radial components. So components either toward or away from the center of the circle. So that would be caused by F sub G and F sub N. Done. Okay, for C, what is the minimum speed he could be going and still make it all the way around the loop without falling off? Okay, so this is the tricky part of the question. Okay, hopefully A and B were easy peasy, okay, if you were solid on your circular motions. Okay, so what's the minimum V? Okay, well, imagine that he was going really fast. Well, to keep him on the circle, F sub N would have to be really quite large because F sub G doesn't change, right? So if he were to go slower and slower and slower and slower, well, then you wouldn't need as much, because remember, V squared is proportional to F sub C, and F sub C is equal to the sum of those two forces. So as you go slower and slower and slower, well, you don't need as much F sub N to make you follow the circle anymore, right? The number of newtons that centripetal force is becomes smaller and smaller and smaller. And so you want to look at the minimum condition is where he is just barely staying in contact with the top of the loop, right? Because if he's not going slow enough, he does like he does in the movie and just falls onto the ground or onto the bottom of the loop. And so you want the condition, sort of the tipping point, is when he's starting to come out of contact with the road or the loop. And so F sub N is essentially, near as makes no difference, 0 when he's at the minimum speed. And when you think about it like that, the mathematics become really quite easy. You don't need to know his mass. You write out, you multiply both sides by r, you take the square root of both sides, and you get that v, minimum v, is just equal to the square root of g times r. And when you shove those values in there, you get 7 meters per second for this set of numbers. Okay? So the tricky part of this question really is down to that, realizing that that is going to be the condition for minimum speed. And if you get that, well, then you're all set. And if you don't, well, if you got this far, hey, you're like halfway there, right? Roughly speaking. All right, see you for the next one.